Okay, this is the second video on the photoelectric effect, and in this video we're going to try and explain what we saw in the experiment. So if you remember, at the end of video 1 we'd seen that the ultraviolet light had caused the effect in the zinc, but visible light hadn't, even though the visible light had greater power. So what we've got here now is a close-up of the metal here, represented by the grey outline. Embedded in the metal we've got the electrons, and the electrons are represented by these little orange blobs. A very simplistic model, I'm sure you'll agree, but anyway, it works. So up until now we've thought of light as actually a wave. So here's our wave of ultraviolet light coming in. Now we know that the electrons could absorb the energy of that ultraviolet light, and they got enough energy to leave the surface of the metal. That's what caused the electroscope to discharge. When we used the visible light, which we'll represent again with our green wave, when we used the visible light, the electroscope didn't discharge, and that was a little bit odd because if you remember back, our visible light was a 100 watt light bulb, and it was producing much more energy per second, so more energy was arriving at the surface of the metal, but the electrons weren't absorbing that, and that was a little bit odd. Scientists couldn't explain that for a long time. In fact, it took someone of Einstein's intelligence and creativity to come up with an explanation. We know that ultraviolet has a higher frequency than visible light. So the model that Einstein used to explain the photoelectric effect was that rather than a continuous wavefront, the ultraviolet radiation, the electromagnetic radiation coming in, consisted of particles or photons of light. So each of these represents one photon of ultraviolet radiation. And I've drawn them as little swiggly waves. It's a good way of representing them because they still have some wave-like properties as well as particle properties. The energy of each photon depends on the frequency of the radiation. So ultraviolet has a higher frequency than visible, so these photons of ultraviolet radiation have more energy than the visible ones. So how does that explain our 100 watt powerful, lots of energy, visible light bulb? Well, the explanation for that is that what we had with our visible lights were lots and lots of very low energy photons. So there were lots of them, so the total energy was quite high, but because the frequency is low, energy depends on frequency, because the frequency is quite low, the individual photon energy is not enough to get an electron to come away. So these electrons absorb the energy of the photon, but because the energy depends on frequency, our low frequency visible light doesn't have as much energy. We can get 100 watts just by shining lots and lots of these weak photons at there, but none of the photons have enough energy in themselves to cause the electrons to be liberated. A good analogy for this is firing ping pong balls at Tony. There's Tony. Okay, give us a smile, thank you. If I fired a stream of ping pong balls at Tony, it would be quite amusing but annoying for him. But we could fire them at him all day long and he wouldn't move. He'd flinch a little bit, but it's not going to knock him off his feet firing ping pong balls at him all day. Oh, there's one just gone off his head there. So you can think of these as the very low energy visible photons. Lots of them, so the total energy is quite high, but in themselves none of these photons have enough energy to dislodge Tony from his position, in the same way that none of the visible photons have enough energy to dislodge an electron. If we increase the brightness, the intensity, all we're doing is making more low energy photons. We're still not going to dislodge an electron, there's just more of them. Okay? One way we could dislodge Tony, of course, is to get rid of our ping pong machine and replace it with a cannon. And the cannon balls are certainly going to get Tony to move if they hit him. So we can think of the cannon balls as UV photons. Okay, not many of them, but each cannonball has lots of energy. Okay, so the total energy might in fact be less than firing ping pong balls at him all day, but each cannonball has more energy, enough to certainly move Tony from where he is now. So the analogy is that the cannonballs represent the ultraviolet photons, high frequency, high energy photons, enough to dislodge the electrons in the same way that the cannonballs are enough to affect Tony. So that explains what happened during our experiment with the photoelectric effect and the gold leaf electroscope. What we're going to do in the next video is have a little look at Einstein's photoelectric equation and how to use that and what everything in that equation actually represents.